Next speaker in this session is Abhishek Mathur. Abhishek, are you there?
Yeah, I'm here.
Can you please share your screen?
Yeah, sure.
Yeah, make it full screen.
Yeah.
Okay, so our next speaker is Abhishek from RI Bangalore, and he'll be talking about space-time entanglement entropy of quantum fluids. You have 12 minutes. I'll give you a reminder at 10.
Yeah, okay, thanks.
Please start.
Yeah, so I'll be talking about space-time formula for entanglement entropy of quantum fields. It's based on work with Sumati and Noman at RRI. So there was a paper by Bombeli, Cole, Lee, and Sorkin, which showed that the entanglement entropy of quantum fields across black hole horizon can be thought of as a source of black hole entropy. So the question arises here is how to measure these entanglement entropy of quantum fields. So one possible answer is to extend the von Neumann definition of entropy from quantum mechanics to quantum field system. But this requires you to compute density matrix at a moment of time. And then you can use this entropy formula to get the entanglement entropy. Now this moment of time, this Cauchy hypersurface may not be found everywhere. Like for example, if we have a topology changing space-time, or in quantum gravity theories like causal set theory, like causal sets, we do not have a notion of Cauchy hypersurface. And therefore, a space-time definition of entanglement entropy will be useful, and that will also ensure covariance. One such definition of space-time definition of entanglement entropy was given by Sorkin himself, and that requires you to restrict the quantum field in a space-time region instead of in a region of space-like hypersurface. There, the entropy is given by this sum over mu log mu, where mu is a solution of this generalized, not solution, mu is the eigenvalue of this generalized eigenvalue equation, where this W is the 2-point correlation function and restricted to the region in which we are restricting the field. I delta is the space-time commutator called as the Poly-Jordan function. And this operation is always well defined if O is compact. O is the region in which we are restricting the field. And whenever O is compact, it's always well defined. These mu, these mu which is used to compute the entropy, they are all real. They come in pairs, like for every mu we have 1 minus mu as another eigenvalue, and it never lies between 0 and 1. That implies that you can write the entropy as sum over mu greater than 1, mu log mu minus 1 log mu minus 1. And you can clearly see that it's always greater than 0 and is equal to 0 only if and only if all mu are equal to 1. Which is the case if the restriction of W to the subregion O is pure. And the restriction is like one case in which the restriction is always a pure state if the Cauchy hypersurface is completely coming inside O. For example, if you look at this picture, if we define a quantum field state in this white cylinder and we restrict it to the green cylinder, since Cauchy hypersurface shown by black circle is completely coming inside this green circle, we'll have the restriction of W to O is pure, and in this case we can easily see that all mu will be equal to 1 if we do a computation here, starting from a pure state. Now this space-time formula of entanglement entropy was used to reproduce Calabrese-Cardy formula, entanglement entropy formula in 2D. So there was this 2D entanglement entropy calculation which was done by Calabrese and Cardy, which used the von Neumann formula. And these papers, there was one by Sir Avni, Sorkin, and Yazdi. They calculated the entanglement entropy for a massless scalar field restricted to defined on this blue diamond, and restricted to this green diamond, which is much smaller than the blue diamond. And they found that the entanglement entropy was of this form, which is exactly same as the one obtained by Calabrese and Cardy. And recently we, along with like me, Sumati and Numan, we studied entanglement entropy of a massless scalar field in a cylinder slab space-time, and restricting it to causal diamond, we also got the similar form similar to that of Calabrese and Cardy. Here we had our field in the SJ vacuum state, which I won't be talking about, which depends on the height of the diamond. Here there is the plot of our findings. So this is entropy versus the size of diamond, and each curve is for different height of the slab. So in these two cases, we see that we get back exactly the Calabrese-Cardy form, and it's comparing well with the von Neumann entropy formula. Okay, yeah. In order to compute with compare the spacetime entanglement entropy with the von Neumann entropy formula, you need to restrict the field to the domain of dependence of this spatial subregion A. And here the spatial subregion, there is a spatial subregion which is arc on a circle, and its domain of dependence is this diamond in which we are computing the space SSCB. Now we come to this spacetime entanglement entropy in de Sitter, which is our recent calculation. So here we consider a massive scalar field to be in Bunch-Davis vacuum state in a conformal patch, which is region 1 union 3. And we restrict it to the static patch, which is region 1, and compute the entanglement entropy there. I mean, space-time entanglement entropy there. Here we note that this region 1 static patch is not compact. But we see that as long as the region of interest is static and spatially compact, we can do our calculation and compute compute mu and the entanglement entropy. So we use the Bunch-Davis modes in this region 1 union 3, which is conformal patch, and static modes in 1. And our calculation should not depend on this static mode, but we use it because they are L2 orthogonal as well as Klein-Gordon orthonormal. So it's easier to do calculation with this mode. And this Bunch-Davis mode defines our vacuum. So the Weitman function, the 2-point correlation function is this. Here we have omitted the LM indices. So there's this phi KLM. Here we have omitted LM. It's there on the side. It's not playing any role in the calculation. This Weitman function can be written in terms of, so the restriction of Weitman function to this subregion 1 can be written in terms of the modes of subregion 1, and I delta we have in terms of modes of subregion 1. And since they are also delta function L2 orthogonal, we can easily compute the, I mean, we have the ingredients, we can easily now compute the eigenvalues, which are found to be these pairs. So like, as you can see, one is mu p minus is 1 minus mu p plus. So these are the eigenvalue. Now there is a degeneracy because there is an LM sitting along with that. There are like infinite LM, and we have to take a cutoff in that to make it well defined. And the mode-wise contribution of the spacetime entanglement entropy is then this. So it's just one mode of like, yeah, I'm computing this object. So this is the mode-wise contribution to the spacetime entanglement entropy. And this is exactly same as the one obtained by Higoshi and Yamamoto in their recent 2018 paper. So here also we see that the spacetime formula which Sorkin had in his paper agrees well with the von Neumann entropy. And this calculation can easily be generalized to any static spacetime region with compact spatial hypersurface. We don't have to consider de Sitter. So for example, if I consider a static patch of short style de Sitter black hole, we can easily generalize this calculation to that case as well. So we did the calculation here. We compute the entanglement entropy in region 1, which is static patch. These are the black hole horizon, HB plus future horizon and HB minus past horizon, and these are the cosmological horizon. So restricting from region this 1 union 3 to region 1 or across the cosmological horizon, we can like do whatever we want, and we get the same form of entanglement entropy as the one we had in de Sitter, where P tilde is P kappa inverse, where this kappa is different for black hole and cosmological horizons. So here it's how this kappa is coming. So concluding this, we can say like we have a space-time formula for entanglement entropy for a QFT, which is as of now is comparing well with the von Neumann entropy. All ingredients involved, W and I delta, are well defined and have a concrete form for a QFT system. Unlike density matrix, which is which we don't know of that, like which does not have a concrete form. Here this W and I delta have a concrete form, a functional form. Since it is space-time in nature, it can be extended to quantum gravity theories like causal set theories. And there are these 2 papers which has done so. They have computed space-time entanglement entropy on causal sets. And it agrees with von Neumann entropy for a system with finite degree of freedom. Like it has explicitly been shown that for any system with finite degree of freedom, the von Neumann entropy and SSE agrees. It has been shown by Sorkin. But it has not been shown for infinite degree of freedom, particularly uncountably infinite, like the quantum field system that we have. It has not been shown in general for quantum field system, although we have specific examples. General construction is still open. And also we wish to understand space entropy from a QFT point of view, and one can refer to this book by Hollins and Sanders and compare it with this entanglement measures studied by them. Yeah, thank you.
Thank you, Abhishek. And
Yeah.
also thanks for keeping in time.
Okay.
Are there any questions? Shriram, please go ahead.
Hi, Abhishek. Thank you. Can you go to this slide where you had the metric of the de Sitter space-time in a closed form, I believe? It was a 1 over h squared eta squared, and you're able to hear me. So
yeah, I'm able to hear you. I'm not getting this slide. You want
okay.
me?
Sure. Okay. I think it's a couple of slides earlier. Let me just. My question is the measure of maybe later. My question is related to whether there is a time dependence here, right? In the de Sitter space-time, and that's reflected, I guess, in your mode functions. But what if you work with a spatially flat de Sitter line element, like people do it in the context of inflation? What will be your boundary, to calculate the entanglement entropy? Does my question make sense?
If I consider
here it is.
do you mean conformally flat? Yeah.
Yes, that's right. Okay, so what I'm saying is that if you work in the spatially flat representation of the de Sitter line element, okay?
Right. So here we are considering a space-time picture. So, okay. So here we have made a restriction to the static patch, and this corresponds to this hypersurface. Hypersurface which is like a hypersurface like this.
Oh, you are working in a spatially flat thing. So I'm sorry, I misunderstood. But I mean, if I think in terms of yes, you are working in the standard spatially flat case. Where is the I mean, what is the dividing surface for you? I'm not able to understand that.
Hello, can you write your question in the chat box?
Sure, sure. Maybe, yeah,
There is a lag.
I will. Oh, okay. I will just, Rajiv, let others ask him the question.
Yeah,
I
sure.
will just leave a message in chat for him.
Amita, please go ahead.
Hey, Abhishek. For the digital case, you showed the mode functions, which are on the next slide.
Yeah, this one.
Yeah, all these mode functions. But when you did the calculation for the Schwarzschild solution, you do not need the mode functions, or what is the, because the mode functions you showed for the Schwarzschild, they're only on the horizon.
Yeah, right. Right. So basically what we need is not the mode function explicitly, but we need how they are Bogoliubov, like what's the Bogoliubov transformation between these modes.
Okay. Only at the horizon.
That is what that goes into the, like if you just know the Bogoliubov transformation between the modes, it's enough to compute the entropy.
I see. So even in the de Sitter case, you don't need all those details about the Hankel functions and the hypergeometric functions and so on. Will that be correct to say?
We don't need. We need these details to compute the Bogoliubov transformation, and we also need to use the fact that these psi are also L2 orthogonal.
Okay. Okay, thanks.
Yeah. So once we have the Bogoliubov transformation, we can go ahead with computing entropy.
Daud, please go ahead.
Hey, thanks, Rajiv. Abhishek, I just had a quick question. In the last slide, you said that you could apply the same expression, Sorkin's expression, or to causal sets. I just wanted to ask, I mean, how are these quantum fields? Yeah, the third point that you mentioned. So it can be extended theories like causal set theories. So how do you really define the quantum fields there? I can't.
So so the defined on causal sets like retarded function. There is an analog of. Hello.
Yes, I can hear you. Yeah.
Yeah. Okay. So these retarded, an analog of retarded Green's function on causal set, and one use it to construct the field commutator, which we know is the difference between the retarded and advanced Green's function.
Okay.
And they have come up with a notion of vacuum, which is positive part of this field commutator. So like they have a notion of a preferred vacuum, which can be the one I was talking about, SJ vacuum. I've not explained it here, but there is a observer independent approach to quantum field we have been working on.
I see. So okay.
That can be extended to causal sets.
Okay.
You can refer to a thesis by Johnston. He was a student at Imperial College.
Okay, sure. Thanks, Abhishek. I just was wondering because to compute the entanglement entropy, you would need to characterize.
Right.
Okay, fine. Thanks.
So
I'm done.
Okay.
Are there any further questions for Abhishek?
There should be one in chat box. I'm just seeing how to see that question.
The question, Abhishek. My question is, you are working in the spatially flat case, and you, in response to Amitabh's question, you're talking about Bogoliubov coefficients. What are these Bogoliubov coefficients relate to? I mean, what are the modes that they relate? They relate the modes at early times and late times in the de Sitter universe. Is that what you're looking at?
Okay, no. Let's say if you want to relate the modes of, Sorry, I think I need to see the question.
Are you not able to hear, Abhishek?
I mean, it's breaking. The voice is breaking.
Okay,
Maybe you can restate the question if the problem is from my end, Sumati.
I'll have to go to Abhishek's office and tell him what the question is.
No, don't. Okay, no.
Yeah.
No, Abhishek, maybe we can.
I can do the following is, Abhishek, can you hear me?
Yeah, I can hear you.
Okay, so the question that he's asking is essentially what you have a Bogoliubov transformation, which you perhaps have not explained what it is between. What are the modes that you're looking at, which maybe you rush through, but you have to explain. And why is it that the other question that he asked earlier was, are you using the conformally flat patch or are you using the static patch? And if so, why?
Okay. So the Bogoliubov transformation is between the Bunch-Davies modes, which is in the conformal patch, and I mean the restriction of it's between the Bunch-Davies mode in the conformal patch and the static modes in this static patch. So once the field is restricted to the static patch, we can use the modes of the static patch to describe the field. So the Bogoliubov transformation is between Bunch-Davies mode and the static modes of the static patch.
Now, so other question that Sriram asked earlier was, why do you use the static patch?
So static patch here is a domain of dependence of this spatial hypersurface, which like crosses through this spatial horizon. And
yeah, maybe Sumati, we can discuss offline. Abhishek, I have some questions. I can chat with you later. Rajiv, over to you.
Yeah. Are there any other questions for Abhishek? I don't see any raised hands. So if not, let's thank Abhishek and also all the other speakers of this session.